This is Unit 2, Video 1, and in this unit we will talk all about the periodic table, the central document of chemistry. And here you have a dancing Russian to help us celebrate, and we'll give you a lot of information about the periodic table. Some of it you have to memorize, some of it is just for your infotainment. So why do we call the periodic table periodic? That word periodic has the word period in it, but not period like at the end of a sentence, but rather periodic meaning every once in a while. So here it says elements have similar properties at regular intervals. So if we graph something about the elements, for example here it's something called first ionization energy, which we'll discuss, you see a periodic pattern. In other words, it goes up and then falls back down again, up, falls back down again, up, falls back down again. So there's a periodic pattern to this, and this is what a periodic pattern looks like. And a lot of elements will have periodic properties, and that's why it's called the periodic table. Got another dancing Russian. And in honor of Mr. Dmitry Mendeleev, we have named an element. This is Mendeleevium, so 101. Element 101 is in honor of Mr. Mendeleev because he is the first to have arranged the elements in the best order and created the first periodic table that was recognized. He's not the only one that created a periodic table, but it was the first one that was scientifically adopted. In addition to that, he discovered discovered the periodic law, the idea of this being a periodic table, and also predicted undiscovered elements, which usually gives you fame in the scientific world. If you can predict the future, you're like a prophet. A lot of scientists do this. If their theories are correct, then those theories will be able to predict things in the future, which what happened. So feel free to get yourself some sort of piece of equipment, utensil, or a cup to celebrate and to help you be reminded of the contribution of Mendeleev to our knowledge. Now there was another scientist also that's associated with the periodic table by the name of Henry Moseley. He was actually an English chemist or scientist, and he arranged elements by atomic number. Now Mendeleev arranged them by atomic mass, and Moseley actually said some of these elements should be flipped. A good example of this is tellurium and iodine. If you take a look, tellurium has a mass of 127, and iodine has a mass less than that. And this actually occurs on the periodic table a few times, and so he flipped some of these elements that Mendeleev just arranged in order of atomic masses. So that was the difference, and this caused the ordering to be rearranged just a little bit. We only have a young picture of Moseley, and that's because he went to war and actually died in World War II, which is unfortunate for a young chemist, and couldn't grow up to an old age. So this is a lesson: children, do not go to war unless you don't plan to do any chemistry and make any contributions to chemistry. So let's label the periodic table with a few terms. We define groups and families as vertical columns. So here is group 1 or family 1. Periods as horizontal rows. So here is period 5 or row 5. Usually we'll refer to these as groups and periods. Now the periodic table, it could be subdivided into 3 sections. The first section could be called metals. Now most of the elements on the periodic table, about 75% of them, are actually metals. So 3/4 of the periodic table contain metals. Anything to the left of, we call these the stairs. Here they are, kind of dividing the P block in 2. And metals, by definition, are really good conductors of both heat and electricity. They're also malleable. Now this word means they can be molded and usually hammered into sheets. That's why metals are really easy to make into wire, make into sheets, like aluminum foil. It's really easy to do this with metal. And the word ductile means essentially the same thing. This means pulled into wire. Pulled into wire. And that's why a lot of metals are used in wiring. mostly copper, but aluminum is also used in wire. Fancy wire uses gold, so fancy wiring. Okay, these are metals. The second section is nonmetals. There are less of these. They are listed to the right of the stairs, including hydrogen. Notice hydrogen is joining us here. Nonmetals are defined as being brittle. Brittle means they crush easily. So if you apply hammer, for example, to a sample of sulfur, this is the element sulfur, it'll crush into little pieces. That's called brittle. They're also poor conductors of both heat and electricity. And then right in the middle we have semimetals. Now there are 8 of them. If you take a look, they are represented here. Now any element that touches the stairs, these stairs that we've just mentioned, is considered a semimetal, except the element aluminum. Aluminum is technically a full metal, even though it's touching the stairs. It's a really good conductor of electricity and heat. It also is very malleable. We have aluminum foil at home. The rest of them are semimetals, and they are semiconductors. And semiconductors means they conduct and don't conduct at the same time. An example here is silicon. Silicon is widely used in computer chips because it can conduct and not conduct, and that's why it's able to be used as a binary code with the 1, 0, 0, 1s, because these represent conducting and not conducting. The noble gases are on the very right of the periodic table. You should be aware of the location of these, and they are very stable. They are the most stable elements of all, and they are unreactive as a rule. And this is because they have a filled outer shell. And we should make a statement here that all elements want to be like the noble gases. We have these in quotation marks. That's not a scientific term, but they strive to be the same in their electron configuration. So the reactivity of elements will actually be connected to the noble gases. And here you have the 5 most famous noble gases. There are a few more that aren't listed. The first group is called the alkali metals. This is group 1 on the periodic table. These metals are soft, with a low density, and extremely reactive. They'll form a +1 ion, and we'll show this. And they're not found in nature free. Now, why aren't they found in nature as free elements? Because they are very reactive, so anytime you find them, they have already reacted. Here we show an example of one of them. This is the element cesium, or rather rubidium. This should be rubidium. And in contact with water, it instantly ignites. Here we see sodium being cut with a regular knife, really easily cut, and being exposed, a fresh surface of sodium being exposed. The rest of this has instantly oxidized or tarnished because of the extreme reactivity. Now, we're going to give you special names for 4 of these. So group 1, group 2, we've talked about the noble gases here, and we'll do group 17 as well. These 4 groups are actually going to have special names. There are names for the other groups, but we usually don't have them, or we don't talk much about them, but those 4 groups have specific names we want you to know about. So group 1, here they are. Here's lithium, really low density. It floats. This is mineral oil. You can't store it in water, so if it floats in mineral oil, you know it's very low density. Good old lithium here. This is good old sodium. And then we have potassium, and then rubidium, and of course cesium. So francium, the last one, is actually extremely rare. It's actually the rarest element, and so we don't have it up here. Now, every one of these elements can actually react with water. So we have a nice little caption here for you, or not caption, but a little picture for you to enjoy, and maybe get a t-shirt with this printing on it. The second group are called the alkaline earth metals. Now, the reason why the first and the second have this word alkali in them, we'll talk about this a little later, and this is the idea of basic. These metals, when they react with water, actually become basic, or make the solution basic. And so you have an example here. This is calcium. When calcium is placed in water, it also reacts. It sinks to the bottom because it's a little more dense, but it's also higher melting, tougher to melt these than group 1, and they will form a +2 ion, these elements. Here they are, beginning with beryllium. Then we have magnesium, nice big slab of magnesium. We have calcium, we have strontium, and we have barium. And notice these, you can see, are also pretty oxidized because their reactivity is pretty high. And actually reactivity increases as we go down. So barium is the most reactive of these 5 that we show here. Halogens then is the 4th group that we're naming. This is group 17, and these are extremely reactive nonmetals. Now we're in the P block. So why are they reactive? For the same reason that group 1 are reactive. They're reactive because they are really close to the noble gases, as we'll see. So being, in fact, if you take a look at the periodic table, what we have is we have the halogens and we have the alkali metals. This is group 1 and this is group 17. And the important thing is both of these are right next to the noble gases. This is the noble gas group. And so group 17 just needs to gain an electron to become like a noble gas. Group 1 needs to lose an electron to become a noble gas. That's why both of these groups are extremely reactive. Now group 1 actually formed positive 1 ions. Group 17, the halogens, will form negative 1 ions. Here you have an example of bromine reacting, very reactive element in group 17. And here they are. Fluorine is kind of a dark greenish gas, maybe more like brownish greenish. Chlorine is definitely green. Bromine is a red liquid, one of 2 liquids on the periodic table. Iodine is a solid, but it sublimes very easily, so you usually see iodine vapor above the iodine. And astatine is radioactive and actually extremely rare, so we don't have a sample of it here either. Now, here's a question: what is the most common element in the universe, and what's the second most common element in the universe? This is important to know, and I'm about to show you both of these. The first common element is, here it is, the element hydrogen. Notice the element hydrogen is very clear. It's a gas. All right, let me show you the second element. This is the element helium. Now, do not confuse them. Again, once again, this is hydrogen. There it is, and this here is helium. Both elements extremely, extremely common in the universe. Actually, most stars are made of hydrogen and helium. In fact, stars burn hydrogen into helium. That's how it works. All right, don't confuse the two. Hydrogen has physical properties of gases and chemical properties of metals. Now, this is kind of strange, but hydrogen doesn't really belong to any group on the periodic table, so sometimes they'll put him right in the middle. As you'll see, it's obviously a gas, but when it reacts, it actually attains a +1 charge. Now, positive charges are characteristic of metals. All these metals will actually form positive charges, and so hydrogen is able to do that. Non-metals, as you'll see, form negative charges, -1, -2, and that's why hydrogen is kind of a unique element. It's also the only element that does not contain a neutron in its nucleus, so has a lot of interesting, unique qualities about it. The main group elements are the S and the P block. The S block, remember, is on the left of the periodic table. The P block on the right. We call them the main group elements. Oftentimes they'll label them with an A. So this would be group 2A, for example. This would be group 17A. That A refers to the fact that they're the main elements, the A elements. The transition metals are your D block elements. Right in the middle of the periodic table, you've got a lot of D block elements. Now, most of these are metals, and they'll have a kind of a grayish, silverish color. However, there are a few that are colored, and most people recognize them. This is copper. The element copper has a very orange-like color. Obviously, the element gold, everybody recognizes gold, and everybody recognizes mercury because it is a liquid, one of 2 elements that are liquids. Hydrogyrum, which actually means water, silver. So hydro means water, and gyrum refers to silver, so kind of liquid silver. The rest of the elements really look the same. You wouldn't be able to tell the difference between most of these metals just by looking at them. Most of them are, again, silverish. Now, some of them do have a tint, like palladium here has a slight yellowish tint. And then, well, there's one more actually, iron. I forgot to mention iron is also a reddish. So you can actually recognize iron. Most of iron that we see is kind of been modified a bit, so steel looks much like any of the rest of these. Now, there is a group of these d block elements called precious metals, and they're also called noble metals, and this is because they are very unreactive, kind of like the noble gases. The noble gases are unreactive gases, and these are unreactive metals. They include the famous element gold. Now, the reason why these are noble is they're stable. The reason why they're precious is because they're rare. This is because they're rare. If gold was very common on the earth, then we wouldn't make it into a very precious metal. But it's interesting that they're also very stable. So gold is found, for example, in old coffins or old archaeological sites from 3,000–4,000 years ago, and it looks exactly like it did when the Egyptians first put those things in the mummies or in the tombs. So very precious. Silver is also a precious metal. Silver actually reacts quicker than gold, but a lot of these, like platinum, is also very stable. And let's mention something called magnetic properties of elements. This is a concept that we're not going to go too deep into, but it's interesting that the three elements that are magnetic, the most magnetic element that everyone knows about is iron. But there are three of them that are called ferromagnetic, ferro for iron, and they include cobalt and nickel. All three of these will respond to a magnet, a regular magnet, or can be magnetized. Actually, will respond to a magnet, rather, I should say. Ferromagnetically, these are field lines, magnetic field lines. They're oriented already, so they're easy to affect. Now, there are elements that are called paramagnetic. Paramagnetic are elements that can actually be induced to have a magnetic field and then respond to a magnet, but very weak. This is very weak magnetism. And that includes all the rest of the elements, notice. It also includes oxygen. Oxygen, pretty famously and interestingly, is paramagnetic. You can actually get oxygen if you have to make it into a liquid or a solid, and it'll be attracted to a magnet. Very interesting. And then we have diamagnetic or antiferromagnetic, and these will have field lines that are kind of permanently cancel each other out because they're in opposite directions. And so most nonmetals are not magnetic. And there are a few metals that are actually also diamagnetic, so they will not respond to a magnetic field. And then we have this crazy antiferromagnetic chromium, will not cooperate magnetically. So a lot of these properties, you'll notice that there's a pattern to it, and that's the whole point. You can also see the pattern to these elements. And then we have rare earth elements, which include the F block elements. They're rare earth because they are rare in the earth. So neodymium is famous for being able to be made into very strong magnets. And you can get yourself a little sculpture like this that has neodymium magnets, and there's a little gap between here. So very strong magnets are made from neodymium. These have a lot of electrons in them and really interesting properties. A lot of these are actually used in current or emergent technologies, hybrid technologies, and rare technologies. So they're actually important for us to obtain, and include things like praseodymium, dysprosium, terbium, and on. So some of the new environmentally friendly technologies use a lot of these rare earth elements, including cerium. And then finally we have radioactive elements. Anything above 84 technically are considered radioactive. So element 84 being polonium, the nucleus gets so big and unstable that it essentially falls apart on its own. And they decay then into smaller elements. Essentially the nucleus breaks apart into pieces, into 2 or 3 pieces. Most of them decay into helium. Helium is a very common decay product. Here you have plutonium, and plutonium is actually used as a nuclear fuel in the spacecraft that we send off into space. We don't care if it's radioactive. There's no living things on board, and so plutonium is actually used in this case. This is plutonium. Now, there are 2 more elements that are also radioactive, but they're below 84, and we kind of see this pattern of exceptions on the periodic table, and they are technetium, element 43, and promethium, element 61. These are also radioactive, and they're actually unstable, and they don't exist. You have to synthesize them, essentially. And here they are. You can actually see both technetium and promethium, and then are red because they're radioactive, but everything else is technically after polonium. All the rest of these are radioactive. And then we have what are called synthetic elements. Now, a bunch of these are radioactive, but you can find them in nature. The rest of these are synthetic, and scientists, chemists, have synthesized them in the laboratory from doing essentially nuclear experiments, nuclear chemistry experiments. So here they are. Some of them are purely synthetic, and some are extremely rare, but we found them in nature, just traces of them in nature. I mentioned francium being the rarest of all in nature. By rare, I mean it does exist in nature. Technetium, notice, does not exist in nature. It's all been synthesized. So all the rest of these, especially down here, the last 10, 20 elements are definitely synthetic and made by humans. Now, this last slide, let's mention that all elements have been named. In fact, we have gone through 118 elements all the way out here, and they all now have names. So feel free to obtain a periodic table, and don't be ashamed because every element now has a name. Alright, this concludes for us video 1. We'll talk about periodic trends in video 2.